Hey AP Pre-Calc, this is Miss Henry, and today we're going to look at section 2.3, all about exponential functions. Our learning target is I can identify key characteristics of exponential functions. So in math, we study many different types of functions, especially our parent functions. And there's 3 of our parent functions that show up in every math class from Algebra 1 to AP Calc. And these are also featured predominantly on the SAT and ACT. And those functions would be our linear, quadratic, and exponential functions. An example of a linear function would be 2x, quadratic would be x squared, and exponential would be 2 raised to the x power. And exponential functions are some of the most important functions in the real world. They appear in many different places, including population growth, money when you're looking at interest and debt, radioactive decay, spread of disease, and many more examples. And additionally, the SAT will also include many questions that require an understanding of exponential functions. So, in general, our exponential function has the form f of x equals a times b raised to the x power, where a is not 0 and b is greater than 0 and not 1. And here, a represents our initial amount, which would be the same as our y-intercept, and b represents the base or the common ratio. If a is greater than 0, so for both of these we're looking at a greater than 0. If b is greater than 1, that is when we have exponential growth. So we are growing as x increases. However, if b is between 0 and 1, that means our common ratio is smaller than 1, so we get exponential decay. So as x increases, our y value will decrease, getting closer and closer to 0. Then with our exponential functions, they are either always increasing or always decreasing. There will be no switch from one to the other, which also means there will not be a relative maximum or a relative minimum. And then just like they will never switch increasing versus decreasing, they will also never switch concavity, which means there will be no points of inflection, and it will either be always concave up or always concave down. And our end behavior, so as I said, as our input values increase or decrease without bound, our outputs or our y values will either increase without bound or they will approach 0. They will only decrease without bound if a is negative. So in general, the limit as we approach positive or negative infinity is either positive infinity, negative infinity, or 0. So it's going to be positive infinity if a is greater than 0 and b is greater than 1. It will be negative infinity if a is less than 0 and b is greater than 1. And then it will equal 0 as we go to infinity if b is between 0 and 1. So as x approaches infinity, it does not matter if a is positive or negative. If b is between 0 and 1, it will always approach 0. So now we're going to write some limit statements for the end behavior of our exponential functions. So our left limit would be the limit as x approaches negative infinity of our function, and we'll just call this f of x. And as we go to the left, we can see that our y values get closer and closer to 0. And then our left limit, so the limit of f of x as x approaches positive infinity, we can see the right side will increase without bound, so our limit equals infinity. So for that one, we have a is greater than 0 and b is greater than 1. But if we look at example B, based off of the graph, we can see that a is less than 0. And because if we were to reflect it over the x-axis, we can see that it's exponential decay. That means b is between 0 and 1. So our left limit, the limit, and we'll call this guy h of x. So the limit of h of x as x approaches negative infinity. So we're looking at the left end of our graph, and we can see that that approaches negative infinity. Then the right side of our graph, as x approaches infinity, it's going to increase and get closer and closer to 0. So I want you guys to try example C, thinking about what that graph would look like. So it might help if you sketch the general shape of your graph, thinking about, is it going to be growth or decay, and is it going to be above or below that x-axis? So for example 2, it's asking us to determine if the function is increasing or decreasing, and if it is concave up or down. So looking at our graph, we can see that A looks like it's going to be part of a smile, which means it would be concave up. And then because we are decreasing, we're going down as we move from left to right, our function is decreasing. So I want you guys to try part B, and let's look at C. So for C, we know A is greater than 0, which means our entire graph is going to lie above the x-axis. And then B is greater than 1, so we know it's going to be exponential growth. So we know our graph will look something like that, and then we can determine our concavity. So once again, this graph looks like part of a smile, so we are concave up. And then because A is greater than 0 and B is greater than 1, we are always increasing. So just as a reminder, your concave up or down does not have anything to do with if the graph is increasing or decreasing. So you want to think about those two things separately. So our last example, selected values of function f are shown in the table above. Determine if f is linear, quadratic, exponential, or none of them. So remember, when we're looking at a table, first thing we want to do is make sure we have consistent input value intervals, or equal length input value intervals. And we can see that each of our intervals has a difference of 5. So since our change in x's are consistent, we can just look at our change in y values. So if I look from 3 to 5, that would be adding 2. 5 to 9, we would be adding 4. 9 to 17, we would be adding 8. 17 to 33, we would be adding 16. So because that is not the same, it's not constant, this function is not linear. So let's see if it maybe could be quadratic. So we'll look at our second differences. From 2 to 4, we're adding 2. 4 to 8, we're adding 4. 8 to 16, we're adding 8. So since that is not constant, it is also not quadratic. So if it is exponential, then our differences will be proportional. So if we look at our differences, going back to when we were looking at our first difference, we can see that it has a ratio of 2. To get from each term to the next, we would multiply by 2. Or we would multiply that difference by 2. So because of that, that makes this function exponential. So once again, it was not linear since the first differences are not constant. And then it was not quadratic because the second differences were not constant. But because our average rate of change and the change in our average rate of change have a common ratio, we know f of x is exponential. So remember, when we have a linear function, our first difference will be constant. For a quadratic function, the first difference will be linear. And for an exponential function, the first difference will be proportional. So that's what we were looking for, is that proportionality. So next time we'll look at section 2.4, and I'll see you guys in class.